Hey there, tech enthusiasts! Today we're diving into the fascinating world of databases. Now imagine a massive library, but instead of dusty books, it's filled with neatly organized digital information. That's a database in a nutshell. Whether it's your online shopping orders, social media posts, or even this very essay, it all lives in a database somewhere. Databases are the backbone of our digital world. They store, organize, and retrieve vast amounts of information with incredible speed and efficiency. Think of them as the ultimate digital filing cabinets, keeping everything in check. But unlike a jumbled mess of papers, databases have a well-defined structure. They use tables, rows, and columns to store data in a way that makes it easy to find and use. Just like a library card catalog helps you locate a specific book, databases use queries to retrieve the exact information you need. So, whether you're a seasoned developer or just curious about the tech that powers your favorite apps, join me as we explore the inner workings of databases. Let's break down how databases organize information. Imagine each piece of data as a book in our digital library. We use something called tuples. A tuple holds all the information about a single item. For example, each tuple might represent a game, with columns for the game's title, genre, release date, and personal rating. How do we find specific games? That's where keys come in. A primary key uniquely identifies each game. It could be the game's ID number or a unique code. Queries are like search bars for your database. They let you ask specific questions like, show me all the action games released after 2020. Just like libraries come in different shapes and sizes, databases have various models for organizing information. Let's explore some of the most popular ones. Hierarchical databases. Imagine a family tree. They organize data in a tree-like structure with parent-child relationships. Network databases. They allow more flexible relationships like a web of interconnected ideas. Relational databases. These are the most common type, organizing data into tables with rows and columns. Object-oriented databases. They store data as objects with properties and methods. NoSQL databases. They offer flexibility for complex, unstructured data. Just like there are different types of libraries for different purposes, databases come in various flavors to suit specific needs. Operational databases. These are the workhorses of the database world. They handle day-to-day transactions like processing orders, updating inventory, or managing user accounts. It's like the library checkout system, constantly buzzing with activity. Analytical databases. Analytical databases are designed for analyzing large data sets and uncovering insights. They're like the research section of the library, where you can dig deep into data and find patterns. Distributed databases. As the name suggests, distributed databases spread data across multiple servers or locations. This improves performance, scalability, and fault tolerance. It's like having multiple copies of the library catalog distributed across different branches. Cloud databases. Cloud databases are hosted on cloud computing platforms like AWS or Azure. They offer scalability, flexibility, and cost-effectiveness. It's like accessing a vast digital library from anywhere with an internet connection. Centralized databases. Centralized databases, on the other hand, store all data in a single location. This can simplify management but might have limitations in terms of scalability. It's like having one central library that serves an entire city. Graph databases. Graph databases excel at handling relationships between data points. They're perfect for social networks, recommendation engines, and fraud detection systems. It's like mapping out all the connections in a complex network of people or things. Section 5. A three-tiered approach. Peeling back the layers. Now let's talk about how database systems are structured internally. Imagine a three-layered cake, with each layer serving a specific purpose. This is the three-level architecture. This is the bottom layer, dealing with the physical storage of data. It's like the basement of the library, where books are organized on shelves and in specific locations. The internal level focuses on efficiency and performance at the lowest level. The middle layer is the conceptual level. It defines the logical structure of the database, including tables, relationships, and constraints. It's like the library catalog, which provides a logical view of the library's holdings without worrying about the physical location of each book. The top layer is the external level, which provides different views of the data for different users. It's like having different reading rooms in the library, each tailored to a specific subject or audience. The external level ensures that users see only the data relevant to them. This layered approach provides data independence, meaning that changes at one level don't necessarily affect the others. It's like rearranging the books in the basement without disrupting the library catalog or the experience of users in the reading rooms. Section 6. Teamwork makes the dream work client-server architecture. In most database systems, data access follows a client-server model. Think of it as a restaurant. You're the client, hungry for information. The database server is like the kitchen, storing and processing the data you requested. When you want to access data, you send a request to the server, just like ordering food from a menu. The server then fetches the data and sends it back to you. This separation of concerns offers several benefits. Centralized data management. All the data resides on a powerful server, making it easier to manage, protect, and back up. It's like having all the ingredients and cooking equipment in one central kitchen. Improved performance. The server is optimized for handling database operations, ensuring fast and efficient data retrieval and processing. It's like having a team of skilled chefs working in the kitchen to prepare your order quickly. Scalability and flexibility. The client-server model allows for easy scalability. You can add more servers to handle increasing workloads or distribute the database across multiple locations. It's like expanding the restaurant with more kitchens and staff to serve more customers. This collaborative approach ensures that data is readily available to those who need it while maintaining security and efficiency. Section 7. Relational databases, where data finds its match. Now let's zoom in on a specific type of database, relational databases. These are the most widely used databases today, powering everything from online stores to social networks. Relational databases organize data into tables with rows and columns, much like a spreadsheet. Each table represents a different entity, and relationships are established through shared keys. It's like connecting the dots between different pieces of information. For example, in an online store you might have separate tables for customers, products, and orders. The customer table would store information about each customer, the product table would list all the products available, and the order table would track each customer's purchases. The beauty of relational databases lies in their ability to connect these tables through relationships. For instance, the order table would have a foreign key referencing the customer ID in the customer table, and another foreign key referencing the product ID in the product table. This way, you can easily retrieve information about a specific order, including the customer who placed it and the products they purchased. Popular examples of relational database management systems, or RDBMs, include MySQL, a popular open-source RDBMS known for its performance and ease of use. PostgreSQL, another powerful open-source RDBMS known for its reliability and data integrity features. Oracle Database, a commercially available RDBMS widely used in enterprise applications. Section 8. Virtual Private Databases, your data's personal bodyguard. In today's data-driven world, security is paramount. That's where virtual private databases, or VPDs, come in. Imagine VPDs as personalized force fields around your data, ensuring that only authorized users can access it. VPDs are a security feature that allows you to control access to data at the row level. It's like having a security guard standing in front of each row in your database, granting access only to those with the right credentials. Here's how it works. VPDs apply a set of rules or policies to determine which rows a user can see or modify. These rules can be based on various factors, such as the user's identity, their role within the organization, or even the time of day. For example, let's say you have a database of patient records in a hospital. With VPDs, you can ensure that doctors only see the records of their own patients, nurses see the records of patients under their care, and billing staff only see the financial information related to those patients. VPDs offer a granular and flexible approach to data security, ensuring that sensitive information is protected from unauthorized access. They act like invisible barriers within your database, safeguarding your data from prying eyes. Section 9. Data under lock and key. Cryptography to the rescue. Let's fortify our database defenses with cryptography. Cryptography is the ultimate lock and key system, rendering data gibberish without the decryption key. Encryption transforms data into an unreadable format, useless to unauthorized users. Even if accessed, encrypted data looks like a jumbled mess without the key. Hashing creates a unique, irreversible code representing your data. Any change in data results in a different hash value, ensuring integrity. Role-based access control, or RBAC, assigns security clearance levels to users. Define roles and grant specific permissions to each role. Implementing cryptographic measures creates a multi-layered security system. It's like having digital security experts guarding your data.